Hello everyone. Welcome to the Super Index AI Knowledge Series. My name is Manikandan Paneerselvam and you are watching one of our 500 video series on advanced research AI subjects. This subseries is related to reinforcement learning. We have 25 videos regarding this subject. This is the first chapter. We are going to discuss the initial terminologies of reinforcement learning today. Before starting the session, I am willing to introduce my book to the audience. This book is about artificial intelligence and machine learning basics. It is available on the internet. The publisher of the book is S. Chan Publishers, one of India's leading publishers. Okay, let's start the session. Before we understand reinforcement learning, we should first understand what learning is. In human life, we all know that learning means the process that helps us gain specific targeted knowledge. We use different learning techniques such as learning from the instructor, learning from the book, learning by experience, learning by mistake, and learning with the help of a coach or trainer. In the similar way, artificial intelligence and machine learning learn techniques using different methodologies such as supervised, unsupervised, semi supervised, and reinforcement learning. Imagine that the AIML is learning intelligence with the help of the neural weights or simply weights. Don't be confused. Imagine weight means some formula which needs to be understood by the AIML, so that after learning we should apply the learning wherever its learned intelligence skills are required. For example, when we teach men's and women's photos to the AIML, it should teach who a men and women are. After teaching AIML with the help of 1000 images, AIML gets ready to classify the men and women. This is the intelligence. But who trained AIML by images? We all know that this methodology is called the supervised learning. We show that image and the label of that image. Both. When 1000 images are done, our supervision is done. Now AIML is ready to use its intelligence by guessing the image. This is the first method. We supervise the learning method. The second method is unsupervised learning. The name shows that AIML should learn everything by itself. It should understand the features of the element or any image and keep that element or image in some group. We call this as a cluster. It's a group or it's a cluster. For example, when we ask AIML to learn all the stars of the sky, AIML will even learn new stars. AIML will place the name for that star. The third method is semi supervised learning. The name shows that it will use both methodologies. Partially, it used the instructor's help with supervised learning. Then, it learned by itself without the help of the supervisor. We will see all these in detail in different subjects. We also have subjects like advanced deep learning and graph neural networks, where we can discuss unsupervised and semi supervised learning. Now, in this subject, our focus is the fourth methodology. The name is reinforcement learning. What is that? I love examples before starting the definition. One of the successful applications for reinforcement learning is the lunar space lander. When we send our rocket to the space, the moon space lander, which carries a rover, must reach the moon. When it is getting down, the predominant technology we use is reinforcement learning. Okay, imagine you are on this lander and supposed to land anywhere on the moon. However, 90% of the moon surface is unsafe to land on. Most of the missions failed because of this wrong landing. Our Chandrayaan 1 failed because of this. So, 90% of places are unsafe to land in. We should teach landers to land in a safe area when they reach the moon's landing space. The lander must learn quickly to land in an unsafe place. Imagine it takes continuous video or photos and makes decisions based on life. If in the first image it identifies the target as dangerous, it should move to the location 50 meters away from the location. Observe, make decisions, change the place. Observe, make decision, change the place. Observe, make decision, change the place. It keep going. It should choose the landing positions from left, right, down, and finally taking some decisions and moving based on them is called action. AAML or lander is taking action. Based on the action, you get a new position or location called state. Every time we give one value as a reward to the lander. Why do we reward the lander? Motivate and say you are on the right path to reach the target location. One more time, we are rewarding AAML on the state, not to reward for the achievement that it does. Instead, the reward is the motivation point for reaching the goal in the future. Compare with supervised and unsupervised learning. Here we say goal, reward, state, action, etc. etc. Okay, we are not in a definition yet. Just giving this example, we need specific learning with an n number of sequential actions to understand the kind of problems we face in real life. Before we compare it with other learning methodologies and their actual usage, we will see some formal reinforcement learning points. We have agents and environment in all our examples. In the moon landing, the lander is the agent. Imagine the lander is operating by AAML and the moon surface is the environment. We take a specific action based on the environment or current state. Say, move left or right on the moon. Once the agent in the environment takes action, the environment returns the new state. Also, the environment gives one reward. You are near the safe zone. Take 1000 euro, 1000 USD. It is a motivation for the AML that we are going on the right path to reach the secure location. Now, we will compare supervised learning with reinforcement learning. What does supervised learning do? It is a static function. There are no sequential tasks. It's a single task. Once the learning is completed, if we show the picture, it's a rare fox. During training, we never showed this fox image. We showed usual foxes to AAML. If our machine learning model identifies this image label as fox, the learning is super successful. It's prediction job. It's a prediction job. The AML predicted the image category. The label is a label in the label is a single task actually. Even in the learning stage, it is a static function. The major difference between supervised learning and reinforcement learning is time. We had time in natural language processing with recurrent neural networks, which is different from this time. In the recurrent neural networks, we keep shifting our positions from the first English word to the second English word. If you don't know natural language processing and the recurrent neural networks, don't worry. Ignore this. You can learn separately in other videos. Here, the time required for reinforcement learning is different. Say, time 1 is 1000 meters away from the moon, landing at 9:10 am. And time 2 is 800 meters away from the moon, landing at 9:11 am. This movement is the time problem. When the time frame changes, we take images of the moon and decide where to land. Should we move a little right or left? We will apply our actions in the next time frame and get a new start. This will keep moving. This is the first time We have seen this use case in supervised learning. Another example you can take is about your school or college studies. If you keep the target as a final exam, you reach the final exam in multiple steps. We can't use supervised learning if we teach this process as learning to AML. Is that the correct statement? No. We can still use supervised learning for the above mentioned use cases. However, the time complexity, CPU, and memory usage will be infinite. How? Let's see that following concept, then you can understand. Before we discuss this concept, I hope you understand the supervised learning is a static function, only one action, and reinforcement learning is the continuous loop. Say, decide, take action, get a new state, repeat. Take action, take a decision, take action, get a new state, and repeat. Is it funny? In supervised learning, we teach the labels during the training state, and human beings teach the labels. Think of the same logic if we apply it to our use case, the moon landing. You can ask lander to take an image. The supervised model can predict the label. By random, we can move the lander to some other location, take pictures, and predict the label. If you apply this loop, it needs infinite images, no goal, and no connectivity between the loop items. We are not sure whether we will reach the target because we don't have a reward concept to alter our policies and direction. I am tossing a new keyword here, policy. We will see this keyword soon. In supervised learning, we need infinite CPU, memory, uncertain effort, and infinite calls. So we need reinforcement learning to tackle goal oriented, loop based use cases. Dot. Now we will see some reinforcement terminologies. Some of them we have seen earlier. The first one is an agent. The agent is the learner. It is basically our AML. Here, during the moon landing, the lander is an agent. Second, environment. The moon is our environment. The environment is where our use cases are getting used. The next one is the episode. With a simple game example, we can say that the game will be performed again and again with the improvised learning knowledge. This means we reach the goal, but we don't say that the goal is done. With the help of this intelligence, we can perform better in the next game execution. If you apply this concept to our moon landing, an episode means repeatedly changing the lander for different moon locations or multiple landers in multiple rockets. We used reinforcement learning concepts and we reached the goal. We learned a lot and we can apply this learning in the next attempt. This is called an episode in reinforcement learning. The next one is state. At any moment, we can take an image and analyze where we are. If we are playing chess, we can have a different permutation and combinations of the coin set at any moment. This is called state. Coming next, actions. We have many sets of actions in a given state. In our example, we can move the lander to the right, left, or down. We can make a decision and apply it. The applied action is the set. We can have only three actions possible in the moon example. As mentioned earlier, rewards are essential. That is the last part here. Rewards help to change the direction. Rewards help to analyze the future final state. Say you want to have 100 million at the age of 60. This means that you don't need to grow steadily at the age of 30. Sometimes the constant growth doesn't reach the goal. If you work as an employee, you never get the goal. But if you are an employer, you will reach the goal at 60. But in between 30 and 40, you have zero increments. But your strategy is solving the goal, not the current reward. Reinforcement learning also used this final goal concept, not the immediate reward. It doesn't worry about immediate benefits. We will see more profound in the subsequent lessons about this. As I mentioned earlier, the action set is fixed and limited. The state set is enormous. It can be discrete or continuous. Imagine videos are continued. If we write reinforcement learning to the car driving agent, if it takes 100,000 images, fixed number, it is discrete. The car speed is continuous. And we can't fix any finite combinations. State sets can be discrete or continuous. In the moon lander example, the state set is not discrete, it is constant. If we add locations by longitude and longitude like Earth, it can be 2.5, 67.5 or 2.55, 67.57. It's continuous. It may fit anywhere. The following fundamental concept is policy. We denote policy as pi in reinforcement learning. Very simple. Do I need to move left, right, or down? If you ask this question, it depends on the current state. If the current state shows a big rock on the moon, I won't decide to move down. I will move left and see. This is the policy. Policy on is a particular state. Get action based on the policy of the current state. How do we feed this data? Imagine teaching moon lander about this. If we have fixed discrete state, we can give a matrix. Say, if you are in the 80,000 state, you apply this policy. If the state set is continuous, we can have the policy as function. Say, function means for a rock, move right as a policy. The following question comes to the mind. Is that policy every time to move the queen when the king is going to get attacked by the elephant in chess? If the chess master applies the same policy in his lifetime, do you think he is a learning master? I mean, if the person keep applying the same policy for the same state whenever he encounters, is he a learning master? No. Policy needs to be altered by learning. The policy also should be applied by daring random decisions. Imagine a child learning an element at random in a stochastic way. It's a random way. But we can't keep fixed policies always. It is a stupid way. If we find a rock in the image, take any actions randomly. Go left or right. If we keep applying the random, we learn a lot and we never use our intelligence to maximize the rewards and achieve the goal. It means you never win the game. What to do now in this case? People apply a probability here. We also call exploitation and exploration concepts. Sometimes we explore, learn things by random decisions, and exploit, apply our intelligence, old learning to gain repeatedly. We will discuss this in detail in the following classes. Now, this algorithm is named epsilon greedy. This is the probability based algorithm. We have one probability parameter epsilon. We denote as E. We fix one benchmark here. Randomly, we pick some numbers between 0 and 1. Use the random choice concept if the number is similar then the threshold, say for example 0.4. Explore the new choice. Use an intelligent fixed policy if the number exceeds the threshold. Exploit the game by intelligent super policy. In life, we have two choices. You want to go in a known route where you know there you will get one mango 100% sure. In the following seven other routes we never tried, you may get 0 or 100 mangoes. So a random new choice is one option. The known route is the other option. RL says to use both routes by selecting this option at a probability. Sometimes use a known route, sometimes explore the new route, so that in the subsequent episodes you will be the master of the intelligence. Okay, we'll park here. Please continue this series. We have 24 more lessons on reinforcement learning. One more time, S. Chan published this book. This book has been written by me. It's a basic introduction to AIML. Finally, don't forget to subscribe to us, press the bell button, like the video, comment on the video, and share the video. Thanks for watching this lesson. Signing off from Manikandan Paneerselvam.